Thank you very much. So first of all, I would like to thank the organizers for giving me the chance to speak at this workshop. So I've already been here for a week, and it has been wonderful. And I should also say that I have already talked about parts of this, different parts of this presentation in the past at different places. So I'm afraid some of you may be a bit bored by now. Sorry about the repetition. The topic of my talk has some similarities with the last talk of today, in that I'm going to talk about quantum integrable spin chains and how this kind of spin chains can be understood by studying various supersymmetric sectors of different gauge theories, and how we can use techniques from supersymmetric gauge theories to kind of solve the spectrum problem of the superspin chains. I will give a quick overview of the spin chains just to set up the notations and to kind of explain what I'm talking about. So the integrable spin chains, I will assume that it has a G symmetry where G will be GLM/N. Because I should emphasize that the main point of the talk is that we're going to do the things for super spin chains with GLM/N symmetry, because basically everything that I will talk about have already been accomplished for the bosonic spin chains. Okay. And I will also assume closed spin chains, so there will be periodic boundary conditions. So spin chain, by a spin chain, I simply mean that I have a Hilbert space, which is just a tensor product of representations of my symmetry algebra G. And so each representation represents a particular side in my spin chain, and each side also comes with a complex number, the Z1, Z2, ZL, etc., where L is the size of the spin chain. And these complex numbers take values in some Riemann surface C, where C can be any of these three things: the complex plane, the punctured plane, or an elliptic curve. Based on this choice, these integrable spin chains are often referred to as XXX, XXZ, or XYZ. They're also called rational trigonometric or elliptic. So one of the central objects of study in integrable spin chain is the R matrix, which acts on the tensor product of two representations, and it depends on the difference between the complex numbers associated to those representations. And so everywhere when I say difference, I mean difference in the sense of these abelian groups. So they can be difference or divisions. And so the defining feature of this matrix is that it satisfies the Yang-Baxter equation, which is diagrammatically represented as follows. So this is just this is an operator equation where the operator acts on the tensor product of three representations with three different complex numbers, and it represents some kind of braiding of these R matrices. And the whole point is that if we have solutions to these equations, then we can construct an integrable spin chain as follows. So using the Yang-Baxter equation, we can define. So first, we can introduce an auxiliary vector space U, and then using the R matrices. So each intersection of lines represent an R matrix, and so by taking a product of these R matrices and constructing indices for this auxiliary space, we can define an operator called the Mondrian operator, which acts on the tensor product of this auxiliary space and the Hilbert space. And then taking trace over this auxiliary space, I can construct an operator that only acts on my Hilbert space. And the magic of the Yang-Baxter equation is that it allows us to show that these operators, these transfer matrices that we can construct, they commute for any values of the complex numbers assigned to these lines. So when I draw a circular line, that just represents this trace. And this equation tells us that if we expand these transfer matrices in powers of U, then the coefficients, which are just operators in my Hilbert space, they all commute for any values of M and N. So in this sense, we have an infinite set of commuting Hamiltonians. If my spin chain is finite dimensional, at some point they will be linearly dependent, but by taking the large size limit of my spin chain, I actually have infinitely many commuting Hamiltonians. And in principle, we can take any element constructed out of this commuting Hamiltonians as the actual Hamiltonian defining my spin chain dynamics, and it will commute with everything else, and hopefully we can diagonalize all of them simultaneously. As we have already seen that in this integrability story, a large role is played by this kind of very large algebras, the Youngian, or they're closely related cousins, the quantum affine Youngian or the quantum elliptic algebras. And they arise as follows from the transfer matrix. So here I was expanding this transfer matrix after taking the trace in power series of U, this U, this spectral parameter. But we can also expand the monodromy matrix itself before taking the trace. So the expansion will look something like this. So here the coefficients will have some index correspond that acts on the auxiliary space. And we can also show that using Young-Baxter that these monodromy matrices satisfy these RTT equations. So here, this intersection is an R matrix, so this R matrix, and these rest constitute these monodromy matrices. And this is a simple application of Young-Baxter where you can take this cross and move it all the way to the other side. Now, so if I have the expansion of this T's such as this, then this equation imposes some constraint on the algebraic structure of these coefficients. And it turns out that this algebraic structure precisely defines the Youngian of G. Well, so whether it's the Youngian or the quantum affine or the quantum elliptic algebra, that depends on in which space these complex numbers take values, whether it's C or the C star or the elliptic curve. Yeah, so again, so as it was already mentioned in Thomas's talk, that these Youngian algebras act on the Hilbert space of the spin chain, and they create and destroy excitations and generate the whole spectrum of the spin chain. Yeah, and the part of this algebra are these commuting charges, which is also called the Bethe subalgebra. So in some sense, the goal of the story is to find the spectrum of the spin chain, so diagonalize all these Hamiltonians. So what we want to do is diagonalize these transfer matrices. And so this in the algebraic Bethe answers, the diagonalization happens similar to how we find the highest weight representations of Lie algebras. So we start with some ground state, which is the tensor product of all the highest weight vectors in my representations. And so by the way, so they can be finite dimensional or Verma modules. I mean, I guess in principle, they can be more complicated representations. But so far, I only know how to talk about finite dimensional and Verma modules. Yeah, and the eigenvalues of these transfer matrices are excitations over these ground states. And excitations, so we can kind of color the excitations, or we can say that there are different types of excitations. And these types correspond to the simple roots of my Lie algebra, which is the symmetry of the spin chain. And each excitation will come with a rapidity, which is kind of like a momentum. So I have a spin chain, I'm creating some excitation, and this excitation, roughly speaking, moves with some speed along the spin chain, and that information is captured by some complex number. Sorry, could you say that? So if I think about Youngian modules as evaluation modules of GLN, so it's evaluation parameter. Right. So suppose I want to construct an arbitrary excited state, then I will create different numbers of excitations of different types. And so this state will have momenta corresponding to different types of excitations and how many of each type of excitations I have created. So there are two indices. One of them, so this S index, it corresponds to the rank of my Lie algebra. It's the type of excitations. And this other index DS, it counts how many of that type of excitations I have created. Now, for arbitrary momenta or rapidity, the state will not be an eigenstate of my transfer matrix or the Hamiltonians. The condition for them to be an eigenstate is that these momenta have to satisfy the Bethe-Ansatz equations, which can be written in this form, where this y is something like a potential function, also called the Yang-Yang function, and extremizing this particular function with respect to this momenta gives us the condition that we get an eigenstate. Now, just to get a flavor of what this Bethe-Ansatz equations look like, so actually, we already saw the Bethe equations in the previous talk, so probably I didn't need to add this, but yeah, so I mean, there's no need to look at it too carefully. I just wanted to give an idea of what the equations look like, basically. So let's see. So some features of this equation is that so it depends on some representation theoretic data. Which representations I have in my spin chain, the spectral parameters associated to the representations. So these are the variables that I'm solving for. So there are equations for each. So for each rapidity, I have an equation because I'm extremizing some function with respect to my rapidities. These A's also encode some representation theoretic data about the, it encodes Lie algebra data. So these are really the entries of the Cartan matrix of G. And since I'm talking about superspin chains, I have a grading, and the square bracket represents grading. So the grading is just that I assign some number 0 or 1 to these integers 1 to m plus n when I'm talking about GLM/n. And it just tells me, well, I mean, GLM/n representations act on graded vector spaces, and this is basically something like the grading of the defining representation. Committing subalgebra. Yes. Okay. How to solve this equation? Also, to be a bit more concrete, what I mean by solving the spin chain is that to be able to compute the R matrix, for example, because as I've shown earlier, that if you have an explicit R matrix, there's an algorithmic way of writing down all the Hamiltonians. Yeah, and the additional parameter that I haven't introduced before are these numbers for each simple root of my Lie algebra, and they are kind of associated to my periodic boundary condition. So they just encode some phase that an excitation picks up depending on which type of excitation it is. So for each type of excitation or for each simple root, I have one of these numbers. And okay, so they have, these numbers can be represented in terms of some. So here I have m plus n minus 1 of these numbers, but they can be represented as differences of m plus n numbers tau, matter of convenience. Okay. All right, so that was what I meant by integrable spin chains. Now, so the main reason that we have these tools of gauge theories that we can use to solve these integrable spin chains is this Bethe gauge correspondence of Nekrasov and Shatashvili. So they have shown that given an integrable spin chain of the type that I have just described, you can construct a supersymmetric gauge theory such that the supersymmetric massive vacua of those gauge theories will be in one-to-one correspondence with the simultaneous eigenvectors of all the Hamiltonians of the spin chain. Okay, so basically, so this is a summary of how we construct those gauge theories. I will later. Yeah. So the idea is that you start with the Dynkin diagram of the Lie algebra that you're considering. So for the bosonic case, there's no ambiguity. There's only one Dynkin diagram. For the super case, there are different Dynkin diagrams depending on the grading that you choose. I am choosing this, in some sense, the simplest one. I can make some comment about what happens if I choose some different one later. Okay, so starting from the quiver, you draw a gauge theory quiver. I mean, I will briefly describe what these quivers mean. So, well, mathematically, they mean they are just regular quivers. But in terms of supersymmetric gauge theory, each arrow represents a matter field, and each circular node is a gauge field or is a gauge group. So here, so the gauge group is UD1 times UD2 times dot 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 UD m plus n minus 1. So these are the ranks. And these square nodes represent flavor symmetry. So in the first quiver, I have SUW1 times SUW2, etc., etc. And there's also a very important U1 overall symmetry, which is not visible from the quiver. Anyway, yes, as I was saying, that each arrow represents a matter field. So this basically represents the matter content of my theory, but in order to completely specify the theory, I should also mention the superpotentials, which are basically some relations between these arrows of the quivers. And so let me quickly kind of describe what the superpotential does. So each loop, let's see. So okay, so perhaps there are different notations of representing the quivers. And I think in one notation, people don't often write these self loops. Now, the only thing that these self loops do is that they impose the moment map, the complex moment map constraint for the action of the corresponding gauge group on the matter field or on the representations of the rest of the quivers. And that's the information about the superpotential that involves these loops. And okay, so how to go from this kind of Lincoln diagram to these quivers. So you basically draw these circular nodes, loops, the framing nodes for all these bosonic simple roots. And for the fermionic simple root, you skip the self loops and instead attach a chiral flavor symmetry. And L is the size of my spin chain. Okay. Now, this quiver was proposed by Nekrasov to study superspin chains with finite dimensional representations. And in our works with Musavian, Raghavendran, and Yagi, we proposed this kind of quivers to study spin chains with Vera modules. And I will roughly refer to both of these kind of quivers by just QDW, where D will refer to the dimension vectors of these quivers and W the framing nodes. Okay. Sorry? No. Yes. So yeah, I did mention it. Yes, it does. But it's not the kind of superpotential where you have the self loop and something quadratic, which would impose a complex moment up equation, which you don't have here. But here you will have a quadratic superpotential involving this loop. And yeah, I think in the mathematical terms of quiver representations, this kind of complicates things. This kind of quivers. A priori, nothing. I mean, there's no obvious relations. I'm just saying that if you want to study superspin chains with finite dimensional representations, you should look at the vacua of the theory defined by this quiver. And if you want to study superspin chains with Vera modules, you look at the vacua of series defined by this kind of quivers. Yeah. Sorry, why I have L's everywhere? No, you have L everywhere, where L is the size of the spin chain. It's not a simplifying assumption. Yes. So the reason that I'm saying that it's not obvious is that there's okay. So these quivers, as far as I understand, they come from some kind of brain constructions, and there are some vague arguments about how you can start from Vera module representations and then specialize to finite dimensional cases. But it requires taking some projections, and the interpretations of those in terms of brains is not super clear. But of course, they're not completely unrelated. Time permitting, I will discuss a bit their brain construction, and hopefully some relations will be apparent. Okay. Yes. Okay. So yeah, that's a very important point. These quivers define supersymmetric quantum field theories with 4 supercharges, but I have not specified the dimension. And the reason is that, as I was saying, that in defining the spin chain, I have the choice of choosing the space of spectral parameters, which can be C star or an elliptic curve. So depending on which one I choose, here I choose as the space-time dimension 1, 2, or 3. So this will be either 1d n equals 4, or 2d n equals 2,2, or 3d n equals 2. It's a quantum version. Yes. Yes, absolutely. That's also true. I mean, you can also describe the vacuum in terms of the equivalent cohomology. Yes. So for the Bethe equations, yes. But there's the more geometric interpretations coming from the Higgs branch description. Yes. What parameterizes the vacuum of the series? Corresponds to the simultaneous eigenvectors of all the commuting Hamiltonians of the spin chain. Yes. Sorry, there's one caveat. I have to vary the dimension vectors. It's not just that. Yeah. Okay, so there's an explicit description later on, but so for now, let me just say that uh, in terms of theories living on brains, so the 1D, 2D, and 3D, they are related by T dualities. So as I was saying, that there's a choice of space C star or an elliptic curve, and in a brain construction, these space will be transverse to the space-time of the series. So if you have a 1D theory and you have a transverse elliptic curve, so this is equivalent to a T-dual theory, which is 3-dimensional. So the underlying quiver variety is the same. What will be different is which cohomology theory you consider, ordinary cohomology theory, K theory, or elliptic cohomology. So so particular basis of the cohomology theory, the stable envelope basis, will literally correspond to the wave functions for the eigenstates of the spin chain. Um, yeah. Yeah. Okay. Yes, it really means 1 errors. Okay. Yeah. So this is kind of the slogan of the Bethe-Gauge correspondence. The initial statement of the Bethe-Gauge correspondence, that the space of massive vacua of the series correspond to the well, not only just the spin chain Hilbert space, but really the eigenbases where all the Hamiltonians are diagonalized. Okay. Yeah. So to get to the Bethe equation, or I mean, to kind of establish this claim, so you turn on twisted masses for all your flavor symmetries. You integrate out the matter content. You generate a one-loop exact twisted superpotential for the vector multiplet scalars. Now, so you can keep track of how many vector multiplet scalars you have. There are some other parameters in the theory, the complex FI parameters. And since we're turning on twisted masses, you break the flavor symmetries by these twisted masses. So, so if the adjoint scalar, so let's say that this whole matrix kind of represents the adjoint scalar in the background vector multiplet, then by turning on masses, you kind of force for this to be into a block diagonal form corresponding to each twisted mass. And then depending on the symmetry breaking pattern, you have the different sizes of these blocks. So you do this for the quiver for the finite dimensional spin chains, and for the other one, you break each UL to the maximal cartons of algebra by turning on twisted masses. Yeah. Yeah. So there. Okay. So the concrete statement is that by space of massive vacua, I mean the appropriate cohomology on the quiver variety. It is the superpotential, yes. So you have to go to the critical locus of the superpotential and then take the cohomology. Yeah, I mean, I should say that Yahao, who is one of my collaborators on this project, he is really the expert on this algebraic geometry stuff. Okay. Okay, so you generate a twisted superpotential, which is a function of all the scalars that you have left in your IR effective vector multiplet. So here I was kind of representing the data that goes into the superpotential. So you have this the twisted masses, and this is a symmetry breaking pattern, which basically the sizes of these blocks, or in case of these handsaw type quivers, so you have the difference between these twisted masses, you have the complex FA parameter, and then you find the vacua by extremizing this equation with respect to these vector multiplet scalars. And the initial statement of the Bethe-Gage correspondence comes from the observation that this vacuum equation is exactly the same as the Bethe-Ansatz equations that we saw earlier. So this twisted superpotential coincides with this Yang-Yang functional of an integrable spin chain. Okay. This is extremely sketchy. The point of this slide is to kind of emphasize the fact that what we just saw is not merely a bijection between two things. Because if you, the Bethe-Ansatz equations and the vacuum equation, they're kind of parameterizing the different vacua and the different eigenstates. So showing that those equations are the same, you can kind of say that, okay, perhaps it's some kind of coincidence that there are the same number of things. But I just want to emphasize that that is not the case. There are more subtle algebraic structures that are kind of compatible between the two things. The trouble is that I am really not an expert on this kind of thing, so I may say something stupid. If I do, please someone correct me. Okay. So the idea is that, so starting from the quiver, so we have the usual construction of the quiver variety. So you look at, so you impose the complex moment map equation. You use some kind of stability condition equationed out by the gauge group. So this defines the quiver variety. Yeah. Yeah. Also, if you don't use a stability condition, you get some kind of stack equation. Now, in some previous lectures at this workshop, we were introduced to cohomological Hall algebras, where we constructed some algebras starting from quivers. Those quivers were not particularly dissimilar to these quivers, but they didn't have these flavor nodes. So one observation is that we can consider extensions of this kind of quiver. So we can consider quiver extensions, where say the middle node and the last node corresponds to those quivers with the same framings, but with different dimension vectors. And since they have the same framing, this this initial node will have zero framing. So this initial node will really look like the kind of quivers that we saw in the lectures of cohomological Hall algebras. And furthermore, the dimension vectors, since this is an exact sequence, the dimension vector would satisfy that the dimension vector in the middle is the sum of the two-dimensional vectors at the ends. Okay. And so from these extensions, we can define two maps. One that goes to kind of the quiver varieties and the ISHTIAQUE quotient for the initial and the final node, and the other into the middle node. And okay, so here's some mathematics going on based on some properties of these maps. So one can argue that we can define a map as follows, where this H, which we define for this initial node, is the equivalent cohomology of the representation space. So if I want to construct a cohomological Hall algebra, I would take a direct sum over all dimension vectors here and define some product. And this other H is just the equivalent cohomology of the Higgs branches. So at the end, what I find is that I should have an action of the coha of my quiver without the framing on the Hilbert space that I construct by taking equivalent cohomology of the quiver and summing over all dimension vectors. So this is just to connect that how this kind of algebras appear in this story. So this cohort doesn't capture the full Youngians. Rather, it captures only half of it, so the raising or the lowering. I think you have to get the full Youngian, you have to add the rest of the stuff by hand. I'm not super familiar with the story. And so, yeah, yes. No, so for 8 superstars, that's a bosonic case. And so then, yeah, it's the usual story of, say the Nakajima quiver varieties as worked out by Molly Kokonkov and a bunch of other people. So that story I'm not super familiar with. Yeah, I mean, it seems similar, but I'm not super familiar with the story, so which is why I'm saying that what I'm saying is literally the Molly Kokonkov story, but I think they're related. I'm not 100% sure. I don't know. Yeah, oh, half, because I mean, it only captures the algebra of, say, all the raising operators. Yeah. Yes, yes, yeah, indeed. Yes, yes. If I have D and W here, I'm not sure what that means. I mean, so the answer is that I don't know, and the reason that I did not consider it is because I really want this H and this H to have the same framing, because for me the framing defines the representation in the spin chain, and I want an algebra action of some kind of algebra on that on the Hilbert space of my spin chain. So I don't want to change the spin chain itself. No, sorry. No, this W is just a framing. Sorry, I misunderstood. Okay. Yeah, I think I did not introduce any notation for the, sorry, I mean this, no, not this differential. Okay, so for the bosonic case, this story was worked on by many people, including Molly Kokonkov, Aganaji Kokonkov, Denishin Konekrasov, Bulimor Zhang, Bulimor Kim, Lukovsky. And I will not have time to explain their different contributions, so I'm just mentioning them now. Okay, and so, yeah, yes, yeah, it does, yes, it does. So that's the part that's kind of I would say, mathematically new and perhaps not well worked out. Yeah, so by the end of the talk, I will make some statement about the elliptic case for finite dimensional representations. And so, yeah, if I don't get to explain everything that I want to explain, um, the main point of this talk is that the story is well understood when there are no superpotentials in the usual sense. So for the bosonic case, or for theories with 8 supercharges. And we have some conjectures for what kind of quivers we should consider if we want representations for super Youngians. And we have some evidence that these kind of quivers really work because we were able to compute, say, the R matrix, the elliptic R matrix following our construction. I guess it kind of differs in the definition. I mean, like if I draw quivers like this, then there are superpotentials. The purpose of the superpotential is to impose a complex moment map. So you can either say that, so forget the loops and just take the quotient of the moment map equation. Well, then there are no superpotentials. You just impose the moment map equation. Or you can say that you have superpotentials, and then you look at the critical locus. Yes, because so these superpotentials, when you have loops, they just impose the complex moment map equation. But when you don't have loops, so here, for example, so here you have a quartic superpotential that couples these 4 fields neighboring to that node. I think they're a bit more difficult to handle because it's not just a simple geometric interpretation. No, I'm going to use the physical argument to compute something, to compute an R matrix, and yeah. I mean, I would say that I'm coming from physics. So using physics, I'm going to compute, say, the wave functions of the eigenvectors of my superspin chains, and then I'm going to claim that this should correspond to elliptic stable envelopes for this kind of queer varieties. And then I'm going to compute R matrix using those basis vectors by computing, again, some quantity in gauge theory, the expectation values of Janus interfaces. No, I'm not relying on the mathematical argument at all. So I'm just saying that this is the kind of argument that should generalize to the super case as well, because we have some evidence from physics. Yeah, and perhaps, I mean, okay, as a physicist, I cannot say how rigorous our arguments are, but perhaps my mathematical collaborator can make a more stronger mathematical statement. Anyway. Okay, so I will be a bit quick. So how do we get to these gauge theories? Yeah, and of course, if you write down the gauge theory, you can observe that your vacuum equations coincide with the Bethe equation, but how do we systematically derive these gauge theories, which should be useful if we want to generalize the story for newer spin chains? So for example, spin chains with Vera modules. And this story goes via another 4-dimensional gauge theories, which is the 4D Chern-Simon theory, introduced by Costello, Buita, and Yamazaki. This is a very simple looking theory. So it basically has the Chern-Simons action. And this is defined on a 4 manifold, which is the product of 2 surfaces. So one is topological and one is a Riemann surface. And so in order to turn this 3 form into a 4 form that you can integrate over this 4 manifold, you plug in the holomorphic volume form on this Riemann surface. Okay. So this theory is topological on sigma and holomorphic on C. And so again, the choices for C are C star, C, or the elliptic curve, as in case of the spin chain. And so this is super trace because I'm considering GLM/n. And as is usually the case in gauge theories, the interesting things to consider in this theory are line operators, extended operators. So the line operators that I will consider are lines in the topological plane labeled by representations of GLM/n, and they have fixed locations in the holomorphic direction. So let's say Z1, Z2, Z3. So as you can see that this data already looks like the kind of data that labels representations in a spin chain. And so what is the purpose of this theory? The most interesting thing is that, so if we compute expectation values of cross line operators in this theory, where I provide incoming and outgoing state, then this computes matrix elements of the R matrix of certain spin chain. And the reason that it is an R matrix is basically that because of the topological invariance, if I have line operators in my theory, I can move them around. And since they have different locations in the holomorphic direction, they never actually collide and you don't get anything weird. So there's no difference between the left-hand side and the right-hand side, which of course is the Yang-Baxter equation. So this is a solution. This is always going to be a solution of the Yang-Baxter equation. Okay, so that's how I want to implement the quantities that I defined in spin chain in gauge theories using this 4-digit Simons. And in order to make connection with Bethe gauge correspondence, I need to construct this 4-digit Simons theory in terms of branes in string theory. So the rough idea is that, so we start in type 2B. Your 10-dimensional spacetime is C, which is the space of spectral parameters, times the cotangent bundle of sigma, which was the topological plane of the 4-digit Simons, and the top nut. And we turn on some background fields in here. And the background fields basically allow you to show that you have a preserved supercharge that squares to not 0, but to a rotation of to an isometry of this background. And the isometry is that it rotates the top nut circle of the top nut. So the right-hand side is kind of a cartoon picture of what's going on here. So here, in addition to this background, I have some D5 branes. And so the top nut, I can think of it kind of as 2 different cigars. So they're 2-dimensional surfaces. And I take, say, MD5s and ND5s, wrapping the 2 different cigars. So because of this non-trivial background, on the D5 branes, what I find is an omega deformed holomorphic topological twist of 6gen equals 1,1 super Young mills. And these 2 branes intersect where these 2 cigars touch at the center of the top nut. So there are open strings stretched between these 2 stacks of D5s. And these open strings, they are localized at the intersection of the 2 D5s, which is the C times sigma. So there I have a twisted version of 4D equals 2 theory of just bifundamental hypers. Yeah, so these are coming from these open strings. And it's kind of like a side comment, or some alternate version is that starting from here, I can T-dualize the top nut circle, which then gives me an NS5, which is a dual of this top geometry. And then I have some D4s ending on the NS5 from different sides. So if I further T-dualize parallel to both NS5 and D4, sorry, this is a typo. This should be D3. This should be D3. This is NS5. So then you have some 4-dimensional theory with gauge symmetry, 4-dimensional theory with gauge symmetry, and some domain wall between them, and some twisted version of this series. And this was the construction of 3D Simons with super Lie algebra symmetry by Mikhailov and Witten. And we also know from the work of Yamazaki that 3D Simons and 4D Simons are related by T-duality. And this T-duality is really this T-duality that I was doing. So you can kind of argue that this D4 brane setup where you have 5D theories with domain walls, so this localizes at the domain wall to 4D Simons theory. But in any case, so we can also arrive at this conclusion by explicitly doing the omega deformation. So as I was saying that on the D5 branes, we have some twisted 6G theory living on sigma times C times cigar, and they localize to 4D Simons with GLM or GLN gauge group on sigma times C. Because I'm working equivalently with respect to the cigar part, so I'm considering everything that's kind of localized at the center of the cigar. And this was done by Costello and Yagi. So when we have both of these theories, UM and UN theory, then we can show that the effective description of the theory that lives on sigma times C. So this includes fields coming from this GLM 4D Simons, this GLN 4D Simons, and the 4D equals to hypers that were already there, coming from the open strings. And so if we can explicitly write down the effective action as in a cohomological sense, and we can look at the BRST non-trivial part, which can be written neatly in terms of these newly defined fields, which includes the GLM connection, GLN connections, and the fermions coming from the 4D equals to hypers. And they form the connection, the super connection for GLM/N gauge group. And the action we can observe that is the Fortune-Simons action for the GLM/N gauge group. Okay, so we have a brane construction of our super Fortune-Simons theory. Now, in order to compute R matrices, for example, we need line operators or crossing line operators. And these line operators are created by introducing more branes. So I understand that at this point, perhaps it's not super intuitive to follow the picture. I mean, follow the kind of this kind of notation. But hopefully the pictures will make some kind of cartoon sense. So the idea is that you introduce even more D3 branes, D3 plus or minus, wrapping some line in the topological plane and wrapping the cigars. So their intersection with these 5D branes is three-dimensional, but it's one-dimensional in the topological plane, and the other two dimensions are the ones where I'm working invariantly. So once I localize, these directions will be gone, and I will just have a one-dimensional intersection between Fortune-Simons and some theory coming from the D3 branes. So there will be line operators in Fortune-Simons, at least that part is clear. And this is kind of the picture of what is going on. So I have the D5s, which eventually become the Fortune-Simons. I'm introducing D3s, and they can form bound state using fundamental string stretch between them. Okay. So for example, and we can kind of tabulate all the supersymmetric states in terms of states and representations, for example. So this picture really applies to the finite dimensional case because, they intersect along C times sigma. Yeah. So for example, this picture, this represents a state in the representation of GL5/3 determined by this Young diagram. So there are some combinatorics going on, but not super important. Okay, so then after applying S-duality, which turns D5 into NS5 and fundamental strings into D1s, what we find is that the supersymmetric configurations of the fundamental strings are now supersymmetric configurations of the D1s. And okay, so I'm also doing some Hardy-Witten transition to change this picture into this picture. Now, so we can, to find what the supersymmetric configurations of the D1s is, we should really look at the effective world volume theory of the D1s and find their vacuum. So that's easily done. So we can read up the theory on the D1 branes. This is given by some kind of quiver, well, exactly this kind of quiver. And yeah, so then the job is to just read off the vacuum of this theory, which we can do. Now, so what the space-time dimension is, so here, as I was explaining, that this C part, which is either the complex plane or the punctured plane or the elliptic curve, is transverse to the world volume of these D1s. So depending on whether I have compact directions in C or not, these D1 branes are really T-dual to D2s or T-dual to D3s. So if there are no compact directions, it's just C, then I'm left with a one-dimensional theory. If it's a star, then I really have a 2D n equals 2,2 theory. If it's elliptic curve, this is 2D to 3D theory. So depending on which curve I have different supersymmetric theories, but I can consider their vacuum. Okay, so that story was for finite dimensional representations. For Verma modules, the story is slightly different. So instead of having infinite D3s, we now have semi-infinite D3s. It's basically the same picture, but in order to emphasize that I have semi-infinite D3s, I'm kind of drawing a pseudo 3D picture. So I have NS5 pluses and NS5 minuses, wrapping cigar plus or cigar minus, and D3 plus and D3 minus ending on these NS5s, and the D1s in between. So again, I can read off the theory living on the D1 branes, which gives me this kind of quivers. The dimension vectors will depend on how many D1s I have in between. And I can read off their vacua from the explicit formula for the two-state superpotential. And they coincide with the Bethe-Ansatz equation for the Verma modules. And the highest weights of the Verma modules, they are encoded in kind of the differences between the positions of these D3s in the directions of the spectral parameters, or in the holomorphic direction. So these differences, they can be arbitrary complex numbers, and they encode the highest weights of the Verma modules. Okay. Yes, they are. So here I'm kind of assuming that, I mean, for this particular picture, I'm kind of assuming that they are all ending on different NS5, sorry, different D5s at the end. but you can consider arbitrary configurations. Actually, yeah, so you can look at this whole picture from the perspective of the D3 brains with arbitrary boundary conditions at both ends. And that will kind of tell you that if you want to study this kind of Yangian type algebras or this cohort type algebras, you should look at the quantization of the Higgs branch of this D3 brain theory, which is going to be some three-dimensional theory. And this will connect to kind of the talk by Ruben Frosek, who explained that we can find some solutions to the Yang-Baxter equation or representations of Yangians in terms of two Yang tableaus. And these two Yang tableaus are really encoding the two different boundary conditions of these D3s, one for the NS5s and one for the D5s that you put at the other end. Okay. Okay, so now to the Higgs brane description of this vacua. So if we have a theory defined by these kind of quivers, so first of all, they have a continuous Higgs branch, but when they turn on twisted masses, most of those are lifted. And by some general argument, the wave function for the ground states, they kind of correspond to the equivalent cohomology of these quiver varieties, where the equivalent cohomology is with respect to the maximal carton of the flavor symmetry. The choice of the plane of the spectral parameter dictates which kind of cohomology theory I should consider, whether it's ordinary cohomology, K theory, or elliptic cohomology. All right, so what is the main point of the talk? The main point of the talk is that we have proposals for certain quivers, and if we consider their equivalent cohomology, the appropriate one, depending on which spectral curve we want. I'm sorry. So I think the spectral curve has a different meaning. So I have to remind myself to keep saying that the space of spectral parameters. Yeah, so depending on the choice of the spectral parameters, we should find an action of this kind of quantum groups on this kind of cohomologies. So for C, it's a Yangian acting on ordinary cohomology. For C star, it's quantum affine algebra acting on K theory. And for the elliptic curve, it's quantum elliptic algebra acting on elliptic cohomology. And it's not just that they act in some silly way. I mean, you could say that it's the trivial action, but it's more than that. They act in a non-trivial way, and we can write down a basis which diagonalizes the action of the beta subalgebra of all of this algebra, which is the stable basis, or whatever the analog of the stable basis is for the super case. Okay. So what progress have we made in this direction? So the only progress that we have made so far is for finite dimensional cases. So what we can do is that we can define elliptic stable envelope for SLM/n or for GLM/n, and we can compute the R matrix. So the stable envelopes are supposed to give you the basis in which the beta subalgebra is diagonalized. And the R matrix, if you can construct an R matrix, you can kind of abstractly argue that you can construct a Yangian or these other quantum groups that acts on these equivalent cohomologies, and you can explicitly write down an action in the basis of the stable envelopes. So that's the purpose of doing these things. So as the simplest example, so what do we compute? So let's say we take GL1/1. So then the quiver that we need to consider is these kind of things. Because we want to compute the R matrix, so the R matrix is just a crossing of two line operators. So all we need are two line operators, which is why we have this framing node 2, because this remember that this encoded the size of the spin chain. And then we have this dimension vector, which can be either 0, 1, or 2. If it's larger, then there are no vacua. There are no supersymmetric vacua. Okay. Now so how do we compute the R matrix from this? So this theory, and so we want to do it for the elliptic case, because if we have things for the elliptic, yeah. So let me get back. So let's say that we consider this. So this is for 1, 2. Did I? No, so I didn't draw anything specifically for GL1/1. So, but for example, so this particular, yeah, of course. Yeah, so indeed. So this is for 5/3, right? So okay, so let's see. Where is the quiver? Okay. Yeah. So I'm computing things for the finite dimensional case. So I'm looking at this quiver, right? Um, no, yes. No, no, yes. So let me describe it a bit more. Okay. So it has only one simple root. Yeah. And it's odd. Yes. Yes. Why it's an extension? No, I'm generalizing the construction of Mollikan-Okonkov to incorporate. Um, so Mollikan-Okonkov worked for quiver varieties that were hyperkähler because they were coming from supersymmetric theories with 8 supercharges. But for the super case, you have 4 supercharges there, so your quiver varieties are just Kähler. So you have to modify their construction a little bit to get to the stable envelopes. Yeah, so it's not just right. Yes, and what we have is not specific to this particular quiver, but I think it applies for SLM/N. Am I right? Okay. Right. So this is the quiver. So this, and since we're interested in the elliptic case, it's 3D. It describes the 3D equals 2 theory. So I have D3 brains, and so this framing node is coming from 2 D5 brains, and so recall that these NS5s in a different duality frame, there were D5s where I had 4 Richard Simons. So where these green lines would give us some line operators, and we want, in order to compute R matrix in 4 Richard Simons, we want crossed line operators. So here I'm bending the brains a bit. This is kind of fishy because you have to make sure that this brain bending doesn't break your supersymmetry. But anyway, this is a cartoon. But so now we're looking at this picture from the D3 brain point of view. So from which vantage point we see the locations of these D5 brains as twisted masses for the flavor symmetry. And when I have crossing, the twisted masses change as I move in my space-time of the D3 brain theory. So basically, it's a mass-Janus interface. So ultimately, what I'm computing in this theory is the expectation value of the mass-Janus interface. So I have my 3D theory on an elliptic curve times an interval. I provide some incoming and outgoing states, which are states here and the states here. And so these are states corresponding to the massive vacuum of the theory, which are certain elements of my eigenbases of the spin chain. And somewhere in between, I have a Janus interface, which interpolates between 2 different twisted masses. And so using supersymmetric localization, I can explicitly compute what these expectation values are for different choices of incoming and outgoing states. And I can construct the full R matrix. Now, to get to the stable envelope, you have to. So here I'm using an interface between positive mass and negative mass. So stable envelope corresponds to positive mass and says 0 mass, or 0 mass and negative mass. And yeah, then you change all the states on one side. The other side is fixed. So this is just to show that we can compute the full R matrix in this case. You get something like this, which has some elliptic functions. And to make sure that this is indeed an R matrix that solves the GL1/1 Yang-Baxter, well, we know what the Yang-Baxter equation is. We can just substitute this and show that it is indeed, it solves the dynamical Yang-Baxter equation for GL1/1. So the point of this was just to show that we have a way to do explicit computations, and we can construct the R matrix that we know how it acts on the stable basis. We have a formula for the stable envelopes as well in terms of these theta functions. So that kind of at least from the physics perspective, that's a reasonable argument that why this framework should work to generalize these works of Molly-Cohen curve to super case, for example. Yeah, so that's all I wanted to say. Thank you. Please. As a cohomology class, I think. The dimension as the degree of the degree of. Yeah. You're talking about the middle dimensional, indeed. Yeah. Of course. Yeah. Indeed. Yeah. So one crucial difference between the hyperkähler case and the Kähler case is that in the hyperkähler case, all the fixed points are really isolated points, and the transverse dimension is even. But in this case, the fixed points are not isolated points. So you have to kind of look at the transverse direction of the fixed points. So if you look at the transverse direction, then it kind of looks like the ordinary hyperkähler case. So, but you have to worry about the directions tangential to the fixed points. Mhm. I am not sure. Presume. No. Yeah. So indeed. So in terms of brains, it seems like a continuous process. Right. So for example, I don't know how I would describe this continuously changing the mass in terms of the quiver varieties, for example, right? Because quiver variety is a discrete thing. So you can say that one quiver variety has some kind of map into the other one, but then it just map that you find at the end. I don't know what the intermediate quiver varieties are. But I'm okay. Yeah, I mean, yeah, maybe there's some making sense of it. Yep. Yeah. Sorry. Yeah. I should have mentioned. So that is an open question, and it's the subject of some ongoing work. Well, I think Yahoo is working on it. Is it much more complicated? Okay. Yeah, that will give you the affine version. Yeah. It should be doable. Mhm. Thank you.